This section is about tests about a population mean. So the main one that we're going to talk about is called a one sample t-test. And you've done a one sample t-interval. So this is going to be a similar idea, except it's going to be in the form of a hypothesis test. So it will be a hypothesis test for a mean. And for these, you're going to have to also calculate a test statistic. In the previous section, your calculator had the capability of doing this without a test statistic, but in this one, you're going to have to use it. So our test statistic is going to be a t. Remember that we use t for means and z for proportions. So it will be t is equal to the sample mean minus, I'm going to call it mu sub 0, over my standard error, which is sx over the square root of n. So I'll just label these. So the x bar, remember, is the sample mean. The sx is the sample standard deviation. The n is your sample size. And this mu of 0, that is going to be the value that you use in your hypothesis. And it's actually going to be the mean that you would have used in the previous section when you were doing a normal model. Okay, so this one, the conditions are going to seem pretty familiar. You'll notice with the t-test, it's going to be similar to the t-interval that we did before. My first condition is the random sample condition. My second condition is going to be the 10% condition. And the third condition will be either that n is greater than or equal to 30, or you have a distribution that is kind of close to normal. You can just say a distribution that's not skewed and no outliers. So it's the same idea as what you had before. Okay, so for example 1, I'm going to give you a list of data. So we have a classic Ross station. They claim to play an average of 50 minutes every hour of music. And so you decide to randomly select 12 different hours, and you want to know if there is evidence that the radio station plays less than 50 minutes of music every hour. So what I'm going to do, there's a few ways to go about doing this, but I'm going to start by doing the hypothesis. And my hypothesis, in this case, because I'm looking at a mean amount, I'm looking at a mean amount of 50. You'll notice we're not going to use a p. We're actually going to use a mu. So my null hypothesis would be that they do play 50 minutes of music. The alternative, you'll notice it says less than, is that they play less than 50. Also, I didn't define my variable, so I'm going to say I'm going to let mu be the true average, or the actual mean, number of minutes of music per hour. Okay, so I have my hypothesis. The next thing I need to do, of course, is to check my conditions. So make sure that you're actually checking your conditions. One mistake I see a lot of students do is they get kind of lazy with their conditions and they just write down what the conditions actually are. But in this case, you do need to check them, in every case, actually. So They told you specifically that the hours were selected randomly. So that one's done. And we're going to say that 12 is less than 10% of, you could say either of all hours in the week, or you can say of all possible hours that music can be played. Either of those is sufficient. And our third condition is going to be the distribution. So in order to do that, you're actually going to have to draw a histogram. So what I'm going to do right now is I'm going to kind of do a side thing, and I'm going to take the values that I have here. I will put them into one of the lists in my calculator. I'm going to use one variable statistics, don't forget about that, and I'm going to actually find out a few things about these values. So the first thing I'll find out is that, so you use one variable statistics, your X bar is 47.917. You find out that your standard deviation is going to be 2.811. You also know, you don't need to use a calculator for this, but you know what your N and your degrees of freedom are. The other thing you can do is you can draw a histogram here. So I'm going to go ahead and do that on the side. I kind of ran out of room underneath here, so that's why I'm not, oops, it should look like that. That's why I'm not drawing it underneath the condition. So you'll look at this histogram and you'll notice there are no major outliers. There's maybe a little one, and it's not skewed. So I'm going to say, I'm actually going to move my condition up here. I'm going to say the distribution is not skewed. And has no major outliers. And it's rare that you actually have something that's skewed or has outliers if you're doing a problem in class, unless they're specifically saying why can you not use a t-test on this. So usually the distributions are going to be they're going to be pretty good. Okay, so to recap, we've already done the hypotheses, we've done the conditions, now we have to name our test. So for this one, we are going to use what's called a one-sample t-test. And this is one of the most commonly used ones that you're going to see. So t-tests in general are very useful. So that's our next step. Next, we're going to do our mechanics. The first thing that you're going to do with your mechanics is you're going to find your test statistic, which is your t. So for my test statistic, remember this was my formula. So my test statistic is going to involve the sample mean, which was 47.917, minus the mean that I had from my hypothesis, which I said was 50. And this is going to be over my standard deviation, or my standard error, I should say, which is the standard deviation from the sample over the square root of n. So you'll find that your test statistic is negative 2.567. So that's a good start to have that. Okay, so now what we're going to do is we're going to run our, we're going to find our p-value. And this one's a little bit different. You're going to be using something new today. So my p-value, before we were using a normal model. So a normal model is like our ideal model that's perfect. But unfortunately, when we're working with means, we actually are going to use what's called a t-curve. And the t-curve is going to look really similar to the normal model. If you want, you can draw it. It's generally going to be a little bit thinner than the normal model. So the difference with the t-curve is we're going to have a 50 in the middle. We're going to have 47.917. And we want to know about being less than that. But like I said, this is not a normal model. This is going to be a little bit skinnier than a normal model. If we had an infinite number of degrees of freedom, then it would be normal. But in this case, our degrees of freedom is only 11. So we have to take that into account. And the way that you're going to do this on the calculator is you're going to go to the distribution function on the calculator. What we're going to do is we're going to use what's called the t-CDF. Before we were using the normal CDF. And it only allows you to use the test statistic there. So we're going to go from any small number up to our t-statistic, followed by our degrees of freedom, which is 11. And when you do that, you end up getting 0.013. Also, if on this step you want to use proper notation, we would write this as the probability that our t is less than negative 2.567. That's a good thing to know. So we now have this p-value. And you have to make sure, just double check, make sure it's not two-sided, because if it's two-sided, you would have to multiply it by 2, but it's not. So we end up with a p-value. It's pretty small. You can decide if you want to use 0.01 or 0.05 as an alpha value. If you use 0.01, you would actually fail to reject it here. However, I would generally use 0.05. So the last thing I need to do is write my conclusion. So for my conclusion, I'm going to say because of the small p-value, I am going to reject my null hypothesis. And I'm going to say that because of that, there is going to be evidence that the radio station plays less than 50 minutes of music per hour. So just make sure that when you write your conclusion, you do include, whether you reject or fail to reject, you have to include that the p-value is small or large, and you have to use the context of the problem and say what you found evidence of. So make sure that you put all of those things. In the previous parts, make sure that you do, in addition to the p-value, you need the test statistic, you need to mention the test name, you need to check all the conditions, and you need to write your hypotheses with your parameter defined. So there's a lot of things that you need to do on these, a lot of things to remember. Okay, so for the next example, we are going to actually have a computer printout. And you'll see problems like these quite a bit. They tend to use probably about 5% of the problems on like the AP test will use these printout type things. And you'll see them written in different ways. So go ahead, read through this. What we want to know, first of all, what we're looking at is interpret the standard deviation and interpret the standard error. By the way, so our standard deviation is here. The standard error, they actually calculated it for you, but they did that by taking our standard deviation and dividing that by the square root of 50. And you're welcome to check that if you want to, but you will find that that's what our standard error is. So for this one, they want you to interpret the two of these things. So we've talked a little bit about standard deviation, but we haven't talked about the interpretation of the standard error. So I just kind of want you to understand what they are. So our standard deviation, which is 0.9, what that means is that the widths of the cubes tend to be about 0.09 millimeters from the mean. So we've talked a little bit about that. Just remember that standard deviation is how far your values tend to be from the mean. So these ones are pretty close. 0.09 millimeters is pretty close. So then our standard error, which I'm going to write over here, which is about 0.013, what that means is that if you were to take many samples of size 50, what would happen is that in many of these samples, so many samples, your sample means would tend to be about that far from the mean. So what's going to happen is if your sample size gets larger, standard deviation is just a sample size of 1, but if you have a larger sample size, then your values are going to be closer to the mean. And that's what the standard error is going to take into account. Okay, so for part B, one thing I want you to notice here is that if you see something like, do these data give convincing evidence, or is there evidence of something, or anything along those lines, that is usually a sign that you have to use a hypothesis test. So let's go ahead and go through this. You're welcome to try the whole thing out on your own, or you can just follow along with me. So I'm going to start with my mu is going to be the mean width of cubes. My hypotheses are going to be that my mu is equal to 29.5. The alternative, you'll notice it's different from is what we're looking for. So the alternative is going to be not equal to 29.5. So then my conditions are going to be pretty much the same as before. It does tell you, if you look above, that the supervisor does look at a random sample. And we don't really know how many cubes are produced in an hour, but we're going to assume that there's probably going to be at least 500. So I'm going to just make that assumption. Sometimes if you can't specifically state for a fact that 50 is less than 10% or something like that, sometimes you're just going to have to make an assumption. And this does seem like a logical assumption, so it should be okay, unless it's a really, really slow factory. Our third condition is either that our sample size is at least 30, or that it's approximately normal. Luckily, it's greater than or equal to 30, so we don't have to look at any distributions. So then we're done with the conditions. So now I'm going to say we will use a one-sample t-test. And the first thing I'm going to do is I am going to calculate my test statistic. My test statistic is going to be t equals 29.4846. That's my sample mean right here, my x bar, minus the mean I had in my hypothesis, which was 29.5, over my standard error. You have the option of either writing this as 0.09 divided by square root of 50, but since they actually give you the standard error, you can just write it as is. And you'll find that your t is negative 1.21. So then the last thing I'm going to do is find my p-value. And to find your p-value, second to last thing I should say, I am going to use, once again, the TCDF. However, because I have a two-sided test, I'm going to multiply it by 2. So my TCDF, I'm going to use any big negative number to negative 1.21. My degrees of freedom is 49. The calculator will do all that for us. So you end up getting 2 times 0.116, which gives me 0.232. So that's my p-value. So here I got a very high p-value, and so there's really no way I can reject the null hypothesis. So I'm going to say, because of the large p-value, I fail to reject my null hypothesis. And what that means is that we have no evidence that the width of the cubes is not 29.5. This doesn't necessarily mean that they are 29.5. We just know, we're just pretty sure that we don't have evidence to say that they're not. So just make sure on this, you don't write anything in your conclusion that suggests accepting the null hypothesis, because you're not allowed to do that. So the next part of this problem, and actually I'm going to let you do D on your own, but the next part of the problem asks you to interpret the confidence interval. And if you look at the very bottom, it doesn't really specifically say that this is the interval. But if you look at what we're doing here on this table, it says interval estimate. The interval is actually this very bottom thing. And above it, the estimate is written in the same, it's the same interval, it's just written in a different way. So our interval is going to be 29.529 to 29.5102. So that's our confidence interval. So first of all, we're gonna do a few things. So we're gonna say we are 95% confident that the true mean width is between those two values. And so that's the first thing. The second thing is that they ask you, would you make the same conclusion with the confidence interval as you did with the significance test? So in the previous thing, we were not able to reject the null hypothesis. We had no evidence of the null hypothesis being false. Actually, here, it's the same thing. I'm going to say a few things. So I'm going to say because 29.5 is within the interval, it is a plausible value. And so it's important not to just write that and ignore the question that they asked, because they did actually ask that question and you do need to answer it. So I'm just going to say we make the same conclusion as part B, which is that there is no evidence that the mean width is not 29.5 millimeters. And you'll find that this one, since we use 95% confidence, and I was just assuming that my alpha level was 0.05. They didn't specifically tell me that, but I just generally make that assumption anyway. So you'll find that you will get the same conclusion with the alpha level that corresponds to the confidence interval. And remember that 0.05 does correspond to 95% confidence.